Testing, can you hear me? Testing again, can you hear me? Alright, so I'm going to be reading the statistics book again. Last stream, I was um, trying to learn this chapter, hypothesis testing with two samples. I do not understand how they were calculating the p-values. I need more practice with this chapter, but anyways, I will start studying the next chapter, the chi-square distribution. I've never read anything about this. Well, I've read about this few times before, but I don't remember anything. The notation for the chi-square distribution is x squared df, where df is the degree of freedom, which depends on how chi-square is being used. If you want to practice calculating chi-square probabilities, then use df n minus 1. The degrees of freedom for the three major uses are each calculated differently. For the x square distribution, the population mean is u is equal to df and the population standard deviation is root 2 times df. The random variable is shown as x squared, but may be any case letter. The random variable for chi-square distribution with k degrees of freedom is the sum of k independent square standard normal variables. X square, z1 square, z2 square, z3, zk square. Random variable for a chi-square distribution with k degrees of freedom is the sum of k independent squared standard normal variables. Curve is non-symmetric and skewed to the right. There is a different chi-square curve for each df. The test statistic for any test is always greater than or equal to 0. When df is more than 90, the chi-square curve approximates the normal distribution. For x square 1000, the mean UDF 1000, the standard deviation is 44.7. Therefore, x is approximately 1044.7. The mean mu is located to the right of the peak. In this type of hypothesis test, you determine whether the data fit a particular distribution or not. For example, you may suspect your unknown data fit a binomial distribution. You may use a chi-square test, meaning the distribution for the hypothesis test is chi-square. To determine if there is a fit or not, the null and alternative hypothesis for this test may be written in sentences or may not be stated as equations or inequality, or may be stated as in equations or inequalities. The test statistic for a goodness of fit test is O minus E square divided by E, the sum of that. Observed value, expected values from theory, the number of different data sets or categories. The observed values are data values, and the expected values are the values you would expect to get if the null hypothesis were true. There are in terms of the form O minus E squared divided by E. The number of degrees of freedom is df, number of categories minus 1. The goodness of fit test is almost always right tail. If the observed values and the corresponding expected values are not chosen to are not close to each other, then the test statistic can get very large and will be way out in the right tail of the G square curve. Absenteeism of college students from math classes is a major concern to math instructors because missing class appears to decrease the drop rate. To increase the drop rate, suppose that a study was done to determine if the actual student absenteeism rate follows faculty perception. Faculty expected that a group of 100 students would miss class according to table 11.1. X number of absences per term 0, 2, 3, 5, 6, 8, 9, 11, 12 plus. Expected number of students 50, 30, 12, 6, 2. A random survey across all mathematics courses was then done to determine the actual number of absences in the course. The chart in 11.2 displays the results of that survey. So expected in the actual number of terms, the actual number of students. Faculty expected that a group of 100 students would miss the class according to this table. This is the expectation, and this is the actual number. Determine the null and alternative hypothesis needed to conduct the goodness of fit test. Goodness of fit test is like the actual number of students is very close. The actual number of student being absent is very close to the expected number. Student absenteeism fits faculty perception. The alternative hypothesis is the opposite of the null hypothesis. Student absenteeism does not fit faculty perception. Can you use the information as it appears on the chart to conduct the goodness of fit test? I think yes, we can, right? No? Notice that the expected number of absences for the 12 plus entry is less than 5. Combine that with combine that group with the 9 to 11 group to create new tables where the number of students for each entry are at least 5. Okay. So what about this? What is the number of degrees of freedom? I don't get what point they were trying to make. There are 4 cells or categories in each of the new tables. Number of cells, so 3. 3 degrees of freedom is 3. I don't get what point they were trying to make here. Employees want to know which days of the week employees are absent in a 5-day work week. Most employees would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as in table 11.7. For the population of employees, do the days of the highest number of absences occur with equal frequencies during a 5-day work week? Test at a 5% significance level. Before I do that, I just want to check one thing. I don't understand this point. I don't understand this point. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The result is shown here. For the population of employees, do the days with the highest number of absences occur with equal frequencies during a 5-day work week? Do the days for the highest number of absences so which days of the week employees are absent in a 5-day work week? Null and alternative hypothesis, the absent days occur with equal frequencies. That is, they fit a uniform distribution. The absent days occur with unequal frequencies. If the absent days occur with equal frequencies, then out of the 60 absent days, there would be 12 absences on Monday, 12 on Tuesday, 12 on Wednesday, 12 on Thursday, and 12 on Friday. These are the expected values. So we subtract them, right? And then square and then divide. Minus 15, 12 minus 12, 12 minus 9, minus 9, minus 15 again. The sum is 3. Okay, the sum 12 minus 15 divided by 12, right? That's what they're doing. And they said that the sum is 3. This is the x squared test statistic. Find the p-value, calculate x squared more than 3. This test is right-tailed. The DFs are the number of cells, which is 4. Let me see if Desmos has this. G-square distribution with more than 3. No, degrees of freedom is 4, right? Degrees of freedom is 4, and then x square is greater than 3. 0.5578. Okay, so the purpose of chi-square is to test whether our expected theoretical values matches the given values. One study indicates that the number of streaming services that American families have is distributed as this table: 10, 16, 55, 11, 8. So this is the expected, and this is what we got from our sample. 1% significance level. Okay. So we have count total statistic. Is there a way to do T square more easily? If I do observed and expected, observed and expected, 10 and 66 and 10. No, observed is percent. Observed is 66 divided by 600, right? Because we want the percent. Yeah. So observed, expected is 10. And then I think over here I can write. How do I make an equation? Square divided by expected. Wait, hold on. Let me just open a Python compiler online. Python compiler online. Sorry, it's slow. It's loading very slowly. Okay, I got this. It's been quite a while since I used Python. The observed values, and then we have the expected values. The expected is 10, 16, 55, 11, 8. 10, 16, 55, 11, 8. And then this is frequency 66, 119, 340. 66, 119, 340, 60 and 15. 60 and 15. Where's the help? You know the help that comes in the thing. Is there hold on. You know that little menu that opens like other commands. I'm just testing one thing. Okay. Let's try this one. 66, 119. 340, 60. And 15. And these are the observed values. And then we have the expected 10, 16, 55, 10, 16, 55, 11, 8. So print. Okay, let me see. Let me check one thing. Yeah, we have this, but what if I do um I forgot how to use the filter. I'll just use a for loop. I literally forgot everything. Wait. I in range. I will print I. I think it's length, right? Getting a revision for Python. Yep. And then thing divided by 6 because I will times it by 100. Okay. Sum is 0. Sum less equal minus the expected value square divided by the expected value. Print sum 4.94. So 0.294. No, wait, the degrees of freedom is, yeah, it's 4, right? Test statistic 29.65. Did I do something wrong? This divided by 6. Can let the calculator do the math. For example, instead of 60, enter 0.1 times 600. 60, 96, 300, 3, wait, 60, 96. Where did they get 60 from? Oh, they multiplied every percentage with 600. If I divide every frequency by 600 instead, don't think that would be an issue. Equation is correct, right? It's observed minus expected divided by expected. And since there are 5 observed values, then we have 4. 29.65. So what is the mistake here? It is 66 divided by 600, but I'm also be going to be multiplying it by 100, right? Um, hmm, I'll just print the current value. If I do 0.1 times 600, I would get 60, and then 60 minus 66 is 6. If I do 66 divided by 600 instead, the expected frequency. No, I think this is wrong. I think I have to do it their way. So instead of this, so expected frequency is EX I times it by 600 EF. This is too large. 600. Oh wait, this is a percentage. I have to divide it by 100 first. 29.6464. Yeah, this is the correct now. I see what my mistake was. 29.6464. Okay. Test of independence. Test of independence involve using contingency table of observed values. The test statistic for test of independence is similar to that of goodness of fit test. Observed values, expected values, the number of rows in the table, the number of columns in the table. There are I times j terms of the form of this form. A test of independence determines whether two factors are independent or not. You first encountered the test independence and probability topic. Okay. Suppose A speeding violation in the last year, and B a cell phone user while driving. If A and B are independent, then probability of A and B is equal to the probability of A times the probability of B. B and A is the event that a driver received a speeding violation last year and also used a cell phone while driving. Suppose in a study of drivers who received speeding violations in the last year and who used cell phone while driving, that 755 people were surveyed. Out of the 7,500, 75570 had a speeding violation, 685 did not. 305 used cell phones while driving, 450 did not. Let Y be the expected number of drivers who used a cell phone while driving and received a speeding violation. If A and B are independent, then by substitution, Y divided by 755. Oh, I read this wrong. I thought this was one number. This is not 7. No, no, no. Out of 755, 70 had a speeding violation and 685 did not. Okay, okay. So Y divided by 755 is equal to 70 divided by 755 times 305 divided by 755. So Y is 28.3. About 28 people from the sample are expected to use cell phones while driving and to receive speeding violations. In a test of independence, we state the null and alternative hypothesis in words. Since the contingency table consists of two factors, the null and hypothesis states the factors are independent, and the alternative hypothesis states that they are not independent. Okay, so null hypothesis being a cell phone user while driving and receiving a speeding violation are independent events. So wait. Okay, so if the null hypothesis were true, we would expect about 28 people to use cell phones while driving and to receive a speeding violation. They got 28 from here, right? If the expected and observed values are not close together, then the test statistic is very large and way out in the right tail of the chi-square curve, as it is in a goodness of fit test. The number of degrees of freedom for the test of independence is number of columns minus 1, number of rows minus 1. The following formula calculates the expected number. So column. So row total, column total, total number surveyed. Yeah, I need to see an example. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recurs among community college students, 4-year college students, and non students. Table 11.515 is a sample of the adult volunteers and the number of hours they volunteer per week. Is the number of hours volunteered independent of the type of volunteer? Okay, so wait. Total, row total, column total, total number surveyed. So row total, column total. Shouldn't row total and column total be the same? So wait, from this formula, we get one of the 755 will cancel out. So 70 times 305 divided by 755. Probability of A is 70 out of 70, 755. The number of people in A, number of people in B divided by the total number of people. Okay, we want to test the number of hours volunteer independent of the type of volunteer. So, for example, we are talking about community college students and 1 to 3 hours. Then community college students is 255, 1 to 3 hours is 268. So this times this divided by 839. Is that it? Let's see. The observed table and the question at the end of the problem is the number of hours volunteered independent of the type of volunteer. Tell you this is a test of independence. The two factors are number of hours volunteered and the type of volunteer. This test is always right tail. The number of hours volunteered is independent of the type of volunteered. The number of hours volunteered is dependent on the type of volunteer. Okay. Type of volunteer 1 to 3 hours, 90.75. Oh, this is the average. No, wait, no, this is not the average. What is this? This is 111 divided by 255, right? Or maybe not. What is this? Expected results are in table 11.16. This is a sample. These are observed values. These are how did wait 90 by how did we get the expected value? Table contains the expected values. How did we get this? One, 2, 3 hours. The table contains expected values. The calculation for the expected frequency for the top left cell is 90.57. Row total, row column divided by, okay, so 255 times 298 divided by 839. That is the, oh, that's what I said earlier. Okay, now I understand. This is if they were independent, right? So if this and if the rows and columns were independent, then so do we do this for every single one? We do, right? And then we have to this minus the oh, that would take so long. And then we end up at 12.99. Okay, understood how they did it. Degrees of freedom. 2 times 2 is 4. Okay, understood how they did it, but one exercise would take so long. So we reject the null hypothesis. This means that the factors are not independent. The goodness of fit test can be used to decide whether a population fits a given distribution, but it will not suffice to decide whether two populations follow the same unknown distribution. A different test called the test for homogeneity can be used to draw a conclusion about whether two populations have the same distribution. Calculate the test statistic for the test of homogeneity. Follow the same procedure as with test of independence. The distributions of the two populations are the same, and the distributions of the two populations are not the same. Okay, so that's what homogeneity means, right? Number of columns minus 1. All values in the table must be greater than or equal to 5. Comparing two populations, for example, men versus women before versus after east versus west, the variable is categorical with more than two possible response values. Men and women, college students, have the same distribution of living arrangements. Use a level of significance of 0.05. Suppose that 250 randomly selected men college students, 300 randomly selected women college students were asked about their living arrangements. Dormitory, apartment with parents, and other. Results are shown here. Two male and female college students have the same distribution of living arrangements. So the degrees is 4 minus 1, 3. 4 minus 1, 3. And this time we do 72. This time we are comparing, right? They say it's computed the same way. What do they mean by that? Do we use one of the values as expected? 2, 3. X squared 3. Calculator or computer. Wait, how did they get this? $250 randomly selected men college students and 300 randomly selected women college students were asked about their living arrangements. 300 from here, 250 from here. They need to tell how they calculated this. Press to enter for enter. Enter the table values by row. Quiet, press start. Run the test. It is computed the same way as the test of independence. All values in the table must be greater than or equal to 5. Do we subtract them? Is that what it is? Do we treat one of them as observed and the other one as expected? Okay, wait, let's try that. 72. 72. We will treat this one as expected. Sum is 0. Expected. Expected I. Do I divide it by 250? 250. Expected percentage, observed percentages. OBI divided by 300. I have no clue what I'm doing. OB. No, this isn't it. They say we calculated the same way as the test for independence. Test for independence is like if men and dormitory were, if the gender and the apartment were independent, like that. I want to see how this is calculated. Both before and after releasing so earthquake surveys were conducted asking voters which of the three candidates they planned on voting for the were in the upcoming city council election. Has there been a change since the earthquake? I mean, more people voted, but they won the distribution, right? Distribution of voter preferences was the same, and the alternative is distribution of the voter preferences was not the same. Number of columns is two. How do they calculate this? I don't understand. Three. What if I don't do this? Okay, so they summed all the before and they summed 167 and 214. So sum of this times sum of this divided by the total and that gives you the expected of this, right? They say it's calculated the same way. 300. Okay, let's try. See if that's how it actually works. 250 men. 300. Hold on. In the test of independence, they calculated the thing, calculated all of this. Did they take the average? What did they take? Oh, this minus the observed value, right? This minus the expected value minus the observed. No, sorry, the observed minus the expected, and then they summed it. Okay, let's try this over here because that's what they're saying. It's the same way as the test of for independence. I don't know what that means. So the expected value is 250 um men, women, total men 250, total women 300 for range length men. So we calculate the expected, which is sum, which is total men times this divided by total, right? 250 divided by this. This is the expected frequency, and then the observed frequency minus the expected divided by the expected sum. Right? This makes sense, right? It's not only for this, and then again for the woman. So this divided by the sum of this, the sum of this is there are probably better ways to optimize this, but for now I will focus just on this. Column total. Column total. Total min times column total divided by 550. They were independent. And then the observed minus their square divided by the expected, and then do the same for women. And then what we end up getting is 10.128. Hey, actually, that worked. Yeah, I didn't actually expect it to work. 10.128. G distribution is 3, 0.018. Okay, that actually worked. So that's how we do it. Use the goodness of fit test to decide whether a population with an unknown distribution fits unknown distribution. Use a test for independence to decide whether two variables are independent or dependent. Use the test of homogeneity to decide if two populations with unknown distribution have the same distribution as each other. Okay, right. Is this the same thing? I thought that was the last. No, this is the last chapter. Test of single variance assumes that the underlying distribution is normal. In an alternative hypothesis are stated in terms of the population variable. Test statistic is n minus 1 s squared divided by sigma square. You can think of s as the random variable in this test. The number of degrees of freedom is n minus 1. A test of single variance may be right tail, left tail, or two tail. So we are testing whether it's normally distributed, right? Math instructors are not only interested in how their students do on exams on average, but how their exam scores vary. To many instructors, the variance may be more important than the average. Suppose a math instructor believes that the standard deviation for his final exam is 5 points. One of the best students thinks otherwise. Student claims that the standard deviation is more than 5 points. If the student were to conduct a hypothesis test, what would the null and alternative hypothesis be? Oh, I thought we were going to calculate something. With individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoon is 7.2 minutes. The post office experiments with a single main waiting line and finds that for a random sample of 25 customers, the waiting time for customers have a standard deviation of 3.5 minutes. So, so standard deviation for normally distributed waiting times for customer on Friday afternoon is 7.2 minutes. On a random sample of 25, the standard deviation was 3.5 minutes. Test statistic is this chi squared n minus 1. So chi square of 24 n minus 1 24 times 24 times. Where did it go? 3.5 divided by 7.2. 3.5. Oh no, wait, it's S square. This is standard deviation. Yeah, yeah. This S square. um 24 times that, right? 24 this times this. 24 g square 24 24. uh how do we know which tail we have to calculate? 4.2. So we reject the null hypothesis. 7.2 and then 3.5. So it's the okay, that's why it's on the left. Yeah, okay, fine. I think that's it, right? They have no answers over here. So I will end the stream here then. And yeah, I will see you guys next stream. Bye.